And on behalf of I'd like to welcome you to this webinar on NEHRP Seismic Design Technical Brief number 12, Seismic Design of Cold Form Steel Lateral Load Resisting Systems, a guide for practicing engineers. The Applied Technology Council's webinar program, and it is made possible with the ATC Endowment Fund. The purpose of the ATC Endowment Fund is to support efforts in education. More information about the ATC Endowment Fund can be found on the ATC website. So if you haven't already, you can download the handouts from the Handouts pod on the GoToWebinar control panel. We know that many of you are interested in receiving professional development hours for your participation today. Importantly, if you haven't already, registrants who would like a PDH certificate must pay $25 through the ATC online store by today and must attend the full duration of the webinar. ATC is charging this nominal fee in order to cover some of the costs of hosting this webinar. A link to the ATC online store will be provided to all registrants in an email distributed immediately following the webinar. For those who have already paid the fee and who attend the entire webinar, a certificate documenting PDH hours will be sent by email within 2 weeks. If at any time during the webinar you have questions, please type them in the questions pod in the GoToWebinar control panel. We're planning to have 3 live question and answer sessions during the webinar. The last question and answer session will be the longest, and we'll attempt to answer all submitted technical questions. If not able to answer live, we'll provide written responses to them after the webinar. So now that we've gotten through the housekeeping items, we wanted to start with a quick poll to better understand your because we're only going to keep it open for a short amount of time. So hopefully everyone can see the poll now. Thanks to all of you who have voted. We're getting close. I'm going to hold it up just for a few more seconds. Getting close to 100% response. Okay. I'm going to close it now. And hopefully you can all see the results. So about 11 of you said that you don't have any experience or knowledge about seismic design of cold form steel lateral load resisting systems. 48% of you said limited, 33% of you said moderate, and 8% of you out there said extensive. So the nice thing is I think you're going to find that we will be providing relevant information in this webinar for all of you out there, regardless of your experience level. So let me tell you about your presenter today. His name is Rob Madsen, Associate Principal with Devco Engineering, Inc. in Enterprise, Oregon, where he specializes in the design of cold form steel framing. He serves on the AISI Committee on Specifications and the Committee on Framing Standards, and he currently chairs the Lateral Subcommittee. In 2016, he served as the chair of the Technical Review Committee of the Cold Form Steel Engineers Institute and received that organization's Distinguished Service Award in 2014. Rob was one of the 3 authors of Technical Brief number 12, which is the topic of today. I'd now like to turn the webinar over to Rob. Rob, please go ahead.
All right, thanks, Justin. And thanks everybody for joining in today. I see there's a lot of folks, and it sounds like we've got a wide variety of experience levels here. So hopefully we will be able to present information that is relevant and interesting to everybody. So today I'm going to provide a brief introduction to CFS and CFS lateral force resisting systems. We'll talk a little bit about the history of CFS. We'll outline standards. And a good portion of the discussion today is going to be about analysis and design of CFS seismic force resisting systems, which is the main topic of TB12. Other topics that might be of interest to engineers and others. And as we go along, of course, as Justin said, we'll have question and answer sessions. So jumping in, the design of CFS members and connections is sometimes considered a little more challenging than other materials, but I think the important thing to remember is that basic mechanics still apply. So all of the procedures that structural engineers are accustomed to using can still be used to analyze a CFS structure. Complexities arise, though, in predicting member strength. In particular, complexities include local buckling, which is a buckling of a flange or a web or a stiffener plate between or beyond the corners of the shape. There's distortional buckling, which is a buckling mode where the section distorts, so the corners move relative to each other. And cold form steel lends itself to open cross sections such as C shapes, and the shear center of a C shape falls outside the section. And so the application of load along a flange, for example, you can see in the diagram at the right, can cause torsional stresses if the section is unrestrained. So common CFS construction types include traditional bearing wall structures, with floor joists and roof joists or trusses just resting on load-bearing studs. Podium-type structures where a CFS load-bearing structure is actually built on top of a lower-level podium of some other construction, such as concrete or hot-rolled steel. You see this sometimes, for example, with maybe a hotel or residential-type structure sitting on top of a parking structure. There are also structures with CFS gravity systems that leverage lateral systems of other materials, such as concrete or CMU shear walls, maybe like an elevator or stair core, structural steel brace frames or moment frames. And penthouse structures on the top of taller, maybe concrete or steel buildings are also common, but those are different set of loading and criteria, since they are typically considered elements and components rather than part of the main building structure. So shear walls are one of the most common CFS seismic force resisting systems. We'll talk quite a bit more about shear walls when we get into the analysis and design part of the webinar. Strap brace walls are another common seismic force resisting system. With one nice feature of the strap braced walls is that they just offer a straightforward analysis and design. So just really simple mechanics to figure out the basic force transfers and so forth in a strap braced wall. And then there are also special bolted moment frames, which can be used for mezzanine and platform construction. We'll talk more about those later on also. And with regard to history, so cold form steel structures, particularly in seismic design, have become more mainstream in recent years, but the use of cold form steel for building construction has been around since at least the 1850s in both the US and England. During the California gold rush, CFS houses were advertised as being cheaper than wood and fireproof and could be built in a day. And in fact, the 1933 Chicago World's Fair featured a steel-framed house called the Strand Steel House. So research into the structural behavior of cold form steel started around 1939. It's performed primarily by George Winter at Cornell University under the sponsorship of the American Iron and Steel Institute. Folks who have dug back into not just cold form steel, but a number of structural topics from the 1930s and 40s are probably very familiar with George Winter's name. He did an awful lot of work, but most of the early work on cold form steel was under his direction. So the work by Dr. Winter proved timely as World War II came to an end, and the wartime sheet steel production was able to be converted into domestic use. And then based on all this early research, in 1946, AISI published its first specification called the AISI Specification for the Design of Light Gauge Steel Structural Members. So that was, of course, the predecessor to what is now AISI S100, or what's sometimes called the NAS spec, or just this AISI spec. So in 1947, Dr. Winter published his work on the effective width method, which is essentially a method of predicting the portions of a section that remain effective. Local buckling in a stud, for example, let's say local buckling the flange, doesn't mean that the member has failed. Or stress transfer mechanisms in the section that can provide for significant post-buckling strength. The method that Dr. Winter developed actually in its basic form is still used today for predicting the strength and stiffness of cold form steel members. 1950s and 60s saw the use of gypsum products grow, where gypsum board coupled with steel framing began to find acceptance in fire-resistive construction. And then in the 1990s, we finally started to see some standardization occurring in the industry. Metal Stud Manufacturers Association, MSMA, was one of the first organizations to recognize the benefit of having standard shapes with common names that designers could specify and builders could buy without the need to pre-select a manufacturer. So anybody that was around in the early 90s or before may recall that if you were going to specify metal stud, you kind of had to pick one manufacturer and use their nomenclature and their shapes and their structural data. But starting in 1990, you could finally specify a shape, and it could come from any number of manufacturers with some assurance that the section would be standardized and meet the specific requirements of your design. In 1994, the Light Gauge Steel Engineers Association, or LGSEA, was formed. That's now called CFSCI, or the Cold Form Steel Engineers Institute. And that was formed to disseminate technical information and provide design guidance to engineers. And in 1998, AISI formed the Committee on Framing Standards to develop standards for design and construction specifically related to the cold form steel framing industry. The development of CFS lateral systems has kind of been more recent. And while the material, steel, used in a CFS lateral system is similar to hot rolled construction, there are a lot of significant differences between the design, particularly as they relate to connections. In fact, CFS construction in large part, methods and connection types are more like those you might find in wood framing, including the use of repetitive framing. So you got framing members at relatively tight spacings, like 16 or 24 inches on center. So some of the first research into CFS shear walls was completed by Dr. Renaud Surette at the University of Santa Clara about 1997. Those shear wall strengths were adopted actually in the 1997 UBC, or the Uniform Building Code, which was the predecessor to the International Building Code, IBC. And in 2004, AISI published the standard for cold form steel framing lateral design. That standard included provisions for wood structural panel shear walls, steel sheet shear walls, and also diaphragms. So research on these systems has continued, and the standards have continued to evolve as we've learned more. And in 2007, AISI published AISI S213, which expanded on the 2004 lateral standard. And then in 2015, the seismic provisions of AISI S213 and AIS 110, which was the special bolted moment frame standard, were combined into a single dedicated seismic standard, which was AISI S415. So since that time, S400 has been updated, first with a supplement S116 and then to S420. And these updates reflect what we learned through additional research and input from users of the standard. AISI actually publishes most of the technical standards for the design of CFS members and systems. First and foremost is AISI S100, which is the North American specification for the design of cold form steel structural members. You may be familiar with this document as just the AISI spec or the NAS spec. In more recent times, people have kind of become accustomed to calling it S100. But S100 provides methods for predicting member strength, stability, and also includes provisions for the design of connections. AISI also publishes a number of standards to address industry issues specifically related to cold form steel framing. AISI S21 is a product standard. It addresses material and product requirements for both structural and non-structural members. S202 is the code of standard practice, which addresses design, fabrication, and installation of CFS structural framing. S230 is a prescriptive standard which provides requirements for the design of residential structures up to 3 stories in height. So generally this is not for use in determining engineering designs so much as for unengineered systems where a builder can use the standard without necessarily going through all of the engineering processes. S310 applies to horizontal and vertical diaphragms using profiled steel panels, and it provides the strength and the stiffness of the diaphragm membrane. It doesn't provide design of the full diaphragm system, so keep that in mind if you're turning to S310. All the information you would need to look at the diaphragm membrane and its connection to the structural members is in there, including strength and stiffness provisions, but it won't tell you, for example, how to design a collector, or chord forces and those sorts of things. So those you would refer back to, say, an S240 or an S400 for additional guidance. And test standards for a variety of members and assemblies are provided in the S900 series standards. And these and other standards are available for free download at cfsei.org. I would like to note actually that the printed version of this presentation had an error in that. It was based on where they used to be available. So if you've got your printed version handy, you might cross out the AISIstandards.org and write in cfsei.org. So AISI S240 is the North American standard for cold form steel structural framing, and that was just recently updated in 2020. That update, in fact, became available just a couple of weeks ago. So if you go to that cfsei.org and look for the free standards downloads, you can find the most current version of S240. And S240 consolidated a number of earlier design standards, including standards for the design of wall studs, floors and ceilings, headers, roof framing, and the wind and low seismic design of lateral systems. And when we say low seismic, what we're talking about is seismic design categories B or C with a seismic response modification factor R equals 3. Sometimes folks think that it should be R less than or equal to 3, and it's kind of a weird setup, but it is actually very specifically R equals 3, and there's a few reasons for that with regard to a very particular system in ASCE 7 that uses R equal 3. But for practical purposes, low seismic design category would be or C, R equals 3. If you're there, you can use S240. If not, you've got to go to S400. So the AISI standard most relevant to technical brief TB12 is S400, the North American standard for seismic design of cold form steel structural systems. TB12 happened to be based on S400-15 with the supplement number 1 or S400-15/S1-16. So S400-15 combined the high seismic provisions of S213 and the special bolted moment provisions of AISI S110. One of the goals in developing S400 was to provide clarity and uniformity in the design provisions for CFS seismic systems. Anybody that spent a lot of time digging through S213 might recall that while the provisions were all there, they were sometimes hard to find and not necessarily organized in a way that made it super conducive to understanding exactly what all requirements might be applicable to your particular system. S400 went a long ways towards streamlining that process so that it was just a lot easier to understand what the requirements were and to perform your designs. And that was largely accomplished by specifically defining the designated energy dissipating mechanism for each seismic force resisting system and providing a consistent design approach and language for each of the systems. So S420 is the second full edition of S400 and includes a number of clarifications and a few substantial technical updates. One of the things we did was we provided a better definition for capacity protected components, replaced that definition, replaced lists, what we called at AISI lateral laundry lists of protected items. It was repeated over and over again in various provisions. So it's much easier to read now and understand what parts of your seismic force resisting system require capacity protection. The drift limitations for CFS buildings with concrete or masonry walls, those were updated now to directly reference ASCE 7. And S400 has always used what's called capacity-based design principles, but the specified value of the expected strength factor, omega E, is what we use in S400 for shear walls. In earlier versions were such that overstrength always controlled. So when you were doing a seismic design, S400 would tell you that you could use the lesser of expected strength or forces from the applicable building code with overstrength, but it turned out that overstrength forces would always control. So S400 20 adopted a more realistic approach that determines expected strength based on the expected strength of the seismic force resisting system itself, and additional strength that results from the attachment of finishes such as added layers of gypsum board, plaster, or EIFS. Steel deck diaphragm provisions were also added in Chapter F of S420, including methods that could be used where special seismic detailing is required by the applicable building code. ASTM also publishes a number of standards relevant to CFS design and installation. ASTM C645 and